Hello, everyone. Welcome to LeetCode Problem of the Day for Sunday, April 21st. This problem is called Find if Path Exists in Graph. And so basically, we're given a bidirectional graph with n vertices where each vertex is labeled from 0 to n minus 1 inclusive. The edges are represented as a 2D integer array edges where each edges I, U comma V denotes a bidirectional edge between vertex U and vertex V. Each pair is connected by at most one edge, and no vertex has an edge to itself. You want to determine if there is a valid path that exists from vertex source to vertex destination. Given edges and the integers n, source, and destination, return true if there is a valid path from source to destination, or false otherwise. And so then they give us some examples, which as usual, can be helpful to visualize the problem. And so say we're given a graph like this, right? This is the edge list that we're given, right? We're given 0, comma 1, right? The link between 0 and 1, 1, comma 2, the link between 1 and 2, and 2, comma 0, which links 2 and 0. And so we can see that we have a source of 0, a destination of 2. Those are connected. In the case down here, we had a source of 0 and a destination of 5. 0 is in this graph, whereas 5 is in this graph, and therefore they're not connected. So there's multiple ways to go about this problem. One potential example is to do depth first search. There's also breadth first search. I'm going to opt for a third option, which uses a data structure called disjoint set, because I think it has a very elegant solution to this problem. So in order to do that, Python doesn't have a built-in disjoint set, so we will have to write our own disjoint set class. And I'll probably create a video on how to do a disjoint set and the logic behind it, just solely on disjoint sets. But for now, we'll just do a brief introduction to the disjoint set data structure. And so the first thing is we're going to need a parent array, which is going to be a list of all the numbers from 0 to n minus 1. Basically, it's going to be a list of all the different vertexes in our graph and the parent of their tree. And the trees in the disjoint set sort of tell you whether or not elements are part of the same set. So then we're going to have rank 2, which is just like the size of the tree, right, underneath that element. And that's just going to say it's going to be 1 at the start. So we will do self.rank equals 1 times n, because at the start, before we actually start assembling these tree sets, the trees are all size 1, right? Because there's nothing underneath them. Everything is basically in a tree of just itself. Hence also this list range up here, because it's going to say basically 0, 1, 2, 3, etc., right? Node 0 is its parent, right? Because this is basically just keeping track of the root node of each of these tree sets. And so 0 is its own parent, 1 is its own parent, 2 is its own parent, 3 is its own parent at the start, right? Before we've started assembling the trees, every element is its own parent, is its own root. All right, so now we're going to write the other methods that we need. So find is another one, right? And that basically just says find the parent node. So we say if self.parent I is equal to I, return I, right? If it's its own parent, if it's a root, then we can just return it. Otherwise, the representative of the tree, aka the root, is going to be equal to self.find self.parent I. So basically just travel up until we find the representative. And then to flatten the list, we're going to say self.parent I equals rep. So basically, so we don't have to do this recursion. Again, just set the parent directly equal to the representative. Then, and this is going to be our moneymaker, the union function method. And we're going to say, right, find the representatives of I and j. Basically, find the root of the I and j trees so that we can link the trees together, right? We need to link them at the root. So then we can say if I rep equals J rep, so if the trees have the same representative, we know that these two elements are already unioned, and so we don't need to connect their trees because they're already connected. Otherwise, we want to say if self.rank jrep is less than self.rep, or rank rather, irep. So this basically is just saying which tree is smaller. If the J tree is smaller, then put the J tree underneath the I tree, right? So set its root now, instead of being itself the root, set its new root to the I representative, and vice versa, right? So if the I tree is smaller, then put the I tree underneath the J tree. And if they're the same size, and it doesn't matter which one goes on top, we just have to remember, though, that now the trees are increasing in size. And we have to say, we have to increase the rank then of whichever tree that we put the other tree under. So if we're putting the I tree, in this case, underneath the J tree, then we have to say self.rank jrep plus equals to 1, because they were the same size, right? So imagine you had two trees of size 3. If you're putting the tree of size 3 underneath the root node of the other tree, it's now going to be a tree of size 4. And so you have to update that rank accordingly. Then we'll include one final method just to give us a neat little solution at the end. Not necessarily necessary since it's going to be a one-liner, but it will look cleaner when we write our final code. And we're just going to say return self.find I equals self.find j. This basically just says, right, same thing that we acknowledged up here, right? If these two nodes are the same representative, then they're technically in the same tree and therefore connected. So now we can say in here, disjoint set is equal to disjoint, oh boy, disjoint set n, because we know we have n nodes and vertices here. And then we can loop through all the different vertexes in the edge list. So for u comma v and edges, disjoint set dot union u comma v. And in this way, we connect all the different edges and group them into different sets to see if they're connected. Now, all we have to do is return disjoint set dot is connected source comma destination. Run that to test, and we have a typo. So try that one more time, and it runs successfully, and we'll submit it. And we see that our solution is accepted. So there you go. There's the disjoint set solution for the LeetCode problem of the day for problem find if path exists in graph.